very happy to have Marika Taylor here, and she's going to give our first talk about the symmetries of black holes. Enjoy.
First of all, thank you for giving up your lunchtime and coming and hearing from us. And secondly, thank you to the organisers for giving me the opportunity to talk, which is actually a rare experience in this department to be able to talk about my own research. That's kind of nice. So we're in a maths department. You might not be surprised by this word, symmetries, but you might be a little bit surprised as to what black holes are doing in the maths department. So at the beginning of the talk, I'm going to explain to you a little bit why we study black holes in the maths department. So another thing you may not know is that actually in maths in Southampton, we have one of the largest groups in the world which works on aspects of gravity and string theory. So I present a whole list of names of people here who might be familiar as lecturers: Niels Anderson, Austin Diaz, Austin Dunlop, Ian Hawke, Winho, Lee Jones, Carl Schwarzschild, Andy Bannon, Andrea Smith, Ross Smithers, myself, James Vickers. Plus we've got about 25 researchers and PhD students, so there's about 12 staff. And we work closely with the high energy and astronomy groups in physics. All these people here that I name are actually, their research is based around aspects of gravity and string theory. So what do we study? Well, we're kind of maximally ambitious. We're interested in the biggest phenomena in the universe. So illustrated over here, this is the history of the universe, its evolution over the last 13 billion years. We're interested in extreme phenomena in astrophysics, formation of black holes, neutron stars, emission of things from them. And we're interested in the very small. So this picture up here, you might be wondering what it is. So string theory is the idea that if you look deep inside particles like the electron, you will actually find little vibrating loops of string, that everything that around us is actually made up at a fundamental level of little vibrating loops of string. So we're interested in things from the very, very small to the very, very large. Okay, now, why are we in the maths department? So written in the Student Centre, there are a number of equations which are meant to be sort of inspirational for you. So if we go back to the late 19th century, beginning of the 20th century, and think about quantum physics and electromagnetism, none of the details of which play a role at all in this talk. All I've written down is the equations. So we look at these as mathematicians, and we look at these equations. So written over here on the left-hand side is Schrödinger's equation for quantum physics. Written on the right-hand side, this is Maxwell's equations for electromagnetism. And you can get a very, very long way with quantum physics and electromagnetism just by looking at these equations. Now, without sort of even thinking in too much detail about, what these equations mean or what the symbols are, we can actually notice something immediately, which is that this equation on the left-hand side, we're clearly solving for a function u of x, and we've got a linear differential equation. So if I told you something about your v of x, you would be able to have a crack at solving that based on the maths that you've been taught in the first year, second year. Over here, we've got operators in vector calculus. Those of you in the second year will be learning about these right now. So these things are actually partial differential equations because they'll have time derivatives as well as space derivatives. But again, the important thing is that they're actually linear equations. And so the maths that you need to solve these was well understood over 100 years ago, 150 years ago. It's taught in the first and the second year. And so people who are doing, looking at these kinds of problems, they're using well-established maths. They sit in physics departments and solve these problems. Now, also to kind of give you inspiration, written in the Student Centre are the equations for general relativity. These are really mathematically very elegant. So sitting on the left-hand side here is something which is measuring curvature of space. And sitting on the right-hand side is a tensor which captures the energy and momentum in space. Okay, so we will agree that that's a beautifully simple, elegant-looking equation. Okay. And general relativity has a kind of nice slogans that go with it. So this is a sort of slide made by the LIGO collaboration, who announced they found gravitational waves earlier this year. That the equations that I had on this slide, on the left-hand side I have curvature, on the right-hand side I have something which tells you about the energy, mass, momentum in space-time. And so the slogan is that the matter which sits on the right-hand side of the equation tells the space how it's curved, space to actually explain it to you. The point is here that the maths is rather complicated. So the thing that sits on the left-hand side here, notions of curvature were certainly not well-known to physicists at the beginning of the 20th century when Einstein wrote down these equations. So the notions that were needed go back to the mathematicians Ricci and Riemann, because heard of Riemann. But this is not easy mathematics. This is not first and second year mathematics. And in particular, if you try and work out this elegant looking object on the left-hand side of my equation, well, it's kind of messy, so I just give you one line. So we've got all these indices floating around because it's a tensor, so it's an object with different indices. But actually the thing I want to notice is not really that, because the indices are just a bit of a pain to keep track of. It's something more fundamental than that. So this curvature object is expressed in terms of what we call a metric G. That you can think of as basically a symmetric matrix. So every time you see G here, you're working with a matrix. But what you see is that there are various products here, right? So this is not linear in G. We've got two G's, it's products of G's, and you've got derivatives in various combinations. Okay, so what does this mean? It means that rather elegant looking expression I had actually turns out to be equations which are nonlinear partial differential equations in this metric tensor. The metric tensor is a 4x4 symmetric matrix. And so whilst the expression was rather elegant, it's conceptually elegant, it's actually really complicated to calculate and to prove. Okay, so to illustrate this, let me not go into complexities of curvature, but illustrate it to you with a rather simple toy example. So what do I mean by a nonlinear equation? So here's my equation. The second derivative of the function g plus g squared is 1. Sorry, my font is a bit weird here, but it's meant to be just 1. Okay, so if we didn't have a g squared there, because that was just g, that would be an equation that was linear in g. Because we've got the power of g, it's a nonlinear equation. Now, if you think about techniques, you start thinking about techniques to solve that equation. It's not so easy, because most of the strategies you've been taught won't work. It's a second order equation, it's nonlinear. But it's a pretty simple equation I've written down. So you should actually believe me, you can see, I hope by inspection, that g of x is being 1 actually solves that equation, because the derivative of that is 0, so that term is 0, and that clearly satisfies the equation. So I can spot a special solution of the equation. And now I can play a trick. I can say, well, let's consider g of x, which is just 1 plus a small thing, h of x, where h of x is small. And then let's take this equation and work out the equation we get for h, neglecting terms which are quadratic in h. And I get an equation here, which again, hopefully doesn't look too scary, so that's just again a linear equation. Okay. So what do we learn from my toy example? We learn that, if you have a nonlinear equation and you manage to spot a special solution, you can actually kind of explore the neighborhood around that solution by just changing that solution away from the solution you found a little bit and seeing the equation satisfies. Okay, and so you could go ahead and actually, I think everyone here could go ahead and work out what happens, work out how h of x behaves and so on and so forth. Now, this approach is actually what people did for pretty much the first 50 years of general relativity. So general relativity equations were written around 1915. Pretty much the first 50 years of the theory was based on the approach I just showed you on the previous slide. People could spot some rather simple exact solutions of the equations, and then they could consider just small deviations from those equations, small perturbations, and then get linear equations from them. So this kind of technique, like this, you spot a solution, and then you think about solutions which are kind of almost exactly the solution that you first had. You get a linear equation for your perturbation. That's what people have spent a lot of time doing. Since the 1980s, there's been a lot of progress in solving the equations numerically. So obviously with computers these days, it's much easier just to put things on a computer. Turns out Einstein's equations are not even easy to do numerically because they're rather nasty partial differential equations. general depend on all the positions in space, but if we assume that things are spherically symmetric, again the solution will be a bit similar. Okay, so let's think of the general relativity back in 1915. So this is a picture, of course, of Albert Einstein. So Albert Einstein, in a sense, went through exactly the same logic I just gave you for my toy example. So he's got this rather complicated equations, so complicated I'm not going to write them down. But he argued that if you have a space-time that isn't curved, it's just flat, that would solve the general relativity equations. And how that's analogous to my example is that this 4x4 matrix that he's solving for is just a constant. So in my example, I just had my function be a constant. He found a solution which just had a specific constant. He argued that would solve his equations. Actually, that was a test of his equations for him. And just like in our example, he then considered small perturbations around that solution. But he's solving for a matrix, so his perturbations also have to be a matrix, so Hij. And then he derived linear equations for Hij. Okay, now when you do this, you find your equation satisfies, your perturbation satisfies this equation, which might look a little bit scary. But it's a partial differential equation involving second derivatives with respect to the x, y, and z spatial coordinates. And it involves time derivatives too. And it's got this term here, c, which is the speed of light. Now, that equation might look a little bit scary, but you will come across, if you haven't already come across in lectures, the fact that a wave which is moving in one dimension in the x direction with the time t, moving at speed v, satisfies this equation. So if you see this in lectures, this is what we call a wave equation. And you see, if you compare these two things here, this is really the same equation, right? So let's compare the equation. You see that v here is c in that equation. This was the speed of light. And now we've got things moving in three dimensions, x, y, and z, as well as x. So what he discovered was he could take his equations, he's got a solution when space-time is not curved at all, and then he looks for little ripples around that, little perturbations, and he finds a solution which describes a wave moving at the speed of light. So what he discovered in 1915 is what we now call a gravitational wave moving at the speed of light. This metric tensor describes stretching and squeezing in space-time. And one way to think of this is as follows. So the picture I'm drawing here is, I imagine that I've got a ring of particles, or indeed a ring of metal if you wanted to, just a giant ring of metal. And as that gravitational wave moves through my screen, so it's moving through the screen in that direction, so it's moving transverse to the board. As it moves through, it effectively stretches and squeezes space so that our ring gets distorted, so it gets longer, and then it kind of contracts to be circular again, and then it gets stretched in the other direction, and then it comes back again. And so this is it's very hard to think about what it means for space-time to be kind of stretched and squeezed, but it's much easier to think about it in terms of the effect that actually has on things which are in the space-time. So we've got a metal ring there. That's the effect that gravitational wave has comes through. So Einstein knew about this in 1915. Beginning of this year, 2016, there was enormous fuss in the media because we discovered gravitational waves. So LIGO made their first detection. Actually, the first detection they made was September 2015, so it was last year. So that's 100 years after they'd been predicted by Einstein. And I think he had on the posters for the talk, actually, he had this picture of the LIGO data. I'll explain it in a moment what is actually being shown in that picture. So it's 100 years after they were predicted. So why did Einstein not go out and measure gravitational waves? Well, the first thing you do if you're thinking as a physicist is you think how big things are. So he thought about, he kind of did some back of the envelope estimates, which I could almost sort of explain to you in Newtonian physics. And he thought he only this is insanely small, right? This is totally insanely small. We have no idea how to measure that even now. So he knew there were gravitational waves, but in a sense he would have dismissed it and said, well, gosh, we're never going to see them. Okay, now shortly after Einstein wrote down his equations in 1915, obviously people tried to find solutions to the equation. That's what you do as a physicist. And then you've got your equations, you try to find solutions. And a man called Karl Schwarzschild found us an exact solution of Einstein's equations, and it's simple enough that I can write it down. So I said I was going to give you the solution in terms of a 4x4 symmetric matrix. Okay, we're not going to really worry about too much about it. I'm just saying it's a pretty simple solution. He found it convenient to use spherical polar coordinates. So this is t, the radial coordinate, and then the angles on the sphere. And then we've got this 4x4 matrix, which is quite simple. Okay. So the only parameter that appears in here, apart from the Newton constant, which characterizes how strong gravity is, the speed of light, there's one other parameter, capital M. Now it turns out if that parameter is 0, you just got flat space written in a different coordinate system to before. If that parameter is non-zero, you've got something massive, M is a mass, you've got something heavy sitting at the center of the space-time. Okay. And this is what we now understand as a black hole. Okay. So, sort of intuition of what's going on. I already showed you a picture that if you've got something heavy, it curves the space-time around it. Now, if you have just an ordinary star, you curve the space-time around it, but if you try and throw something off the star, you can still throw something up and it will escape. So we know, you have worked out with sort of Newtonian mechanics, how fast do we need to shoot something off the surface of the Earth so it goes into space, right? That's a fairly straightforward calculation to do. If you make a star smaller and more dense, that escape velocity increases, and that corresponds to the fact that the space-time is more strongly curved around it. So a black hole, in the physics definition, is something for which the escape velocity exceeds the speed of light, and nothing can go faster than the speed of light. So if you're inside the black hole, you're inside the event horizon, you can't escape. So let's do a picture of this. So our sun, a sun is midway through its life. It's an ordinary star. It curves the space-time around it. Clearly, light can escape from the surface of the sun because it escapes and reaches us. There are two stars which are further on in their evolution, things like white dwarfs and neutron stars. The only important thing about them for this book is that they're actually just more dense. They're just smaller. And they've got the same mass, but they would be smaller. And so they curve the space-time around it more. So if you're sitting on the surface of a white dwarf or a neutron star, this is curved, the gravity is stronger. So if I want to throw something up off the surface of a white dwarf or a neutron star, I have to throw it at a higher speed to get it to escape. That's what's being shown in this picture. Now, the logical thing is, if I want to shrink things further and further, so if I take a neutron star and I take the same mass, but I make it even more compact, there'll come a point where actually that escape velocity exceeds the speed of light. And that's when we get a black hole. We illustrate this so that if you're down in this region down here, even if you pump your rocket up so you go at the speed of light, you will not be able to get through that surface. If you're out here, that's fine. You can get out again by pushing towards the speed of light. But if you're down in here, even if you go at the speed of light, you will not be able to escape. Gravity is so strong in a sense that it will just turn you back again. It will just turn you around again. So this is the modern sort of physics way we understand black holes. Now, back in 1916, remember at that time they didn't have very good telescopes. They didn't know much about white dwarfs or neutron stars or stellar evolution, star evolution at all. They didn't know much beyond solar system physics. And people thinking about this, Einstein and Schwarzschild, in any case, they really weren't astronomers, right? That was not what they spent their life doing. So they were actually looking at this from the perspective of a mathematician. So they were looking at this solution of the equations from the perspective of a mathematician. And just, thinking about this without knowing, much in detail, we can see that there's something funny happening in what I've written on the right-hand when the radius takes the value 2 times gmc squared. Because that term clearly goes to 0 there, and that's becoming a 1 over 0. Okay, so as we go to that point, clearly what I've written down is not well defined. So what did they do? Well, they effectively did more sophisticated versions of what's done in, say, 2045 variable theory. They sort of tried to establish whether this was really a problem, or whether they could actually make sense of things, so they could actually make changes. And they realized that they could actually change coordinates, and they could continue through to the region where r is less than that special value. Okay, so essentially they viewed this as mathematicians. They had certain functions, and they asked whether they could actually, certain tensors, they asked whether they could change coordinates, they asked whether they could actually analytically extend functions and make sense of it. And Karl Schwarzschild did this. I mean, his papers from 1916 are very well known. They're very much written from a maths perspective. But I have to say, in 1916, scientists didn't really take this very seriously. So they thought that this solution was absolutely fine for describing the space-time outside of a spherical star. They thought that was a really good description, and it is. This is the same description we'd use for the sun. But they didn't really take seriously the idea that we should go beyond this value of r and go inside and do all these analytic continuations. They thought that was kind of math tricks. And they thought that actually there would just be other things happening in that. So physically, this would just not be the description of what was going on there. Okay, this sort of gradually changed through the 20th century. So the picture on the right-hand side is Chandrasekhar, a great physicist on black holes and astronomy. He won the Nobel Prize in 1983. So in the 1930s, he was one of the first people to really think about what would happen when stars ran out of nuclear fuel. So I said that our star, our sun, is in the middle of its life. So it's got, it's really, there's all kinds of nuclear processes going on in the sun. So it's using nuclear fuel to have nuclear processes. And the kind of balance that happens in a star is that all the particles in the star, they feel a gravitational force which wants to attract them. Okay? But there's nuclear fission going on, and that kind of forces, that creates a pressure. And so there's an equilibrium between the pressure and the attraction. But Chandrasekhar sort of asked the question of what would happen once a star ran out of fuel. So he also started to understand that stars would go through very many periods in their evolution, because as you run out of one type of nuclear fuel, you start burning another type of nuclear fuel, and you keep going on, but eventually there's no kind of nuclear process that can happen. So he kind of understood the evolution, and that the stars darken as they get older and so on and so forth. But when it runs out of nuclear fuel completely, he just couldn't see a physics process which would stop the star collapsing. So gravity would always be there, that was his logic. It would always make the particles attract, but there would be no kind of other process to kind of compete with it. And then the star surface would just collapse inwards. So really from the 1930s onwards, he argued that there really would be black holes. And so he argued sort of to take seriously this kind of picture, and this picture of an object where things inside the event horizon, deeply inside, could not escape. He couldn't see anything that would actually stabilize these things once the nuclear processes had stopped. Now, there's a sort of a long period in the 1940s and 50s where, of course, a lot of physics research was kind of tied up with the war at that time. So people were, of course, interested in developing nuclear weapons. A lot of resources were diverted into that. And it was only sort of into the sort of 60s that people almost literally started looking upwards again, because this was the period of the space race and so on, and people who do fundamental science try and kind of get money from whatever is a political objective of the day. So there was an escalation from the 1960s onwards in our understanding of astronomy as we sort of, again, literally started looking upwards. And really Karl Schwarzschild had proposed from various sources. So a black hole, by its very definition, it doesn't give out visible light of any kind. So your telescopes are not going to see a black hole. You can see a neutron star. You can see a, ordinary stars. You can't see a black hole. So what do they see? So this is a picture on the right-hand side. This is a picture taken by a telescope over a period of years. This is 95 to 99. It's a little bit old now. And you see that they can see visible stars which seem to be going round in orbits. So this one is going around in orbit, and this one is going around in orbit. And things which are further away also seem to be moving around in orbit. So what they're seeing on the telescope is stars orbiting things which are invisible to the telescope. And the thing that's invisible is a black hole. So that they can actually work out, if you actually just look at that orbit and you kind of look up a textbook on Newtonian orbits, you can actually figure out there has to be something really heavy in the middle. Because this is itself a star, right? And it's moving, each year it's moving a huge amount. Okay, so actually if you do the calculation of this, you figure out that the thing in the middle that you can't see has about 20 million times the mass of our sun. It's 20 million times as heavy as our sun. And it's now called Sagittarius A star, this thing. So that kind of tells you that there's something which is very heavy, very small, and you can't see. And that's a kind of indirect evidence that might be. Now, of course, more recently, there's been a lot of effort in trying to sort of measure black holes or see black holes directly. So I said that we didn't expect to see gravitational waves from things that happen in our solar system because they're just too small. But if you run through the same calculation for black holes, then you get much larger gravitational waves. So black holes, I said, are very, very dense objects. They produce much stronger gravitational fields near them. So it's a much more violent, much more extreme sort of process. So this video, which is now an actual simulation of solutions of Einstein's equation, this shows you what happens when black holes collide. So in this picture, the black dots that you see, these are showing the black holes. So actually what's being drawn is the surface of no return. So that's the surface through which nothing can escape. And the thing underneath it, the kind of bluish colour, which is shaded, I think, to make it look nice, this is the effect on the space-time around it. Okay. So we've got these two black holes, they're moving around each other. And what we see here is, as they're moving around, they're causing the space-time to really bump up and down. Right? They're causing it to really wave considerably. They slow the movie at this point because there's a lot more happening. They're looking at detail. This is frozen because now the black holes have collided. They've made just one. And now the black hole is sort of just, basically squeezing and resting. And the purple lines coming out, that's gravitational waves being produced from this process. Okay, so this is a real, as I said, this is a real simulation of solutions of Einstein's equation, which is, this particular one comes from Caltech, but actually we do our own simulations here also. People like Ian Hawke have been involved in this kind of thing. So what we learned from these simulations, and these simulations have been done for at least 20 years, I would say. So if you collide two black holes from each other, with each other, you produce a huge amount of gravitational waves. And so what the LIGO detectors were looking for was really extreme events like this: neutron stars, black holes colliding, the gravitational waves that come from it. And the basic principle they use to detect it is what I sort of explained to you earlier, the idea of kind of looking at how space-time is stretched and squeezed. Now, they have two detectors. They have more being built actually, but they have two detectors. And the reason is that although this is, a really extreme event, still the kind of scale of the effect that we're seeing on Earth is pretty small. And they have to be really sure that what they see in their detectors is not caused by local earthquake seismic activity. So you put one detector in Washington, one in Louisiana, there's one coming in India. If you see the same thing happen happening in all of them, you're confident that it's coming from the sky. If you see an event in one of them but not the others, then you know that that's probably just local earthquake activity. So that's why when you see this data presented, you see the data from the two, and it's important that they look basically the same. They saw the same thing with a time delay because the gravitational waves hit this one before it hit that one, and that tells you where it came from as well. Okay, so what they saw was a collision which happened about 1 billion years ago. Because it happened 1 billion years ago and the waves had travelled a long way to get to us, their amplitude was still pretty small. The black holes that collided each had masses which were about 30 to 60 times the mass of our sun. And I think the most astonishing thing is that the gravitational waves that were given out in the milliseconds of the collision, so I slowed it down in my simulation, it was actually milliseconds, they had 3 times the energy of the sun given out in milliseconds. So this is a truly violent event. And so, possible for quantum purposes. So now, LIGO obviously is sold as massive, breakthrough in the detection of gravitational waves. But from the perspective of somebody who does black hole physics, I think this was underemphasized in the news story. This is the first direct detection of black holes, actually. So it's the first direct detection. Many indirect detections of black holes. This is the first direct detection, and so it probes black holes really a lot more than the indirect things which have been done before. So this, not being able to see it on a visible telescope, but seeing things orbit around it, that's really nice, but that doesn't really tell you what's happening near the black hole, because by definition you can't see it. This, we're seeing the gravitational waves which were formed from the black hole collision. So by looking at those gravitational waves, you can learn a lot about black holes. Okay, so black holes are real. In fact, Stephen Hawking made a bet many years ago with his friend Kip Thorne. Kip Thorne is one of the people who pushed the LIGO detector, the person who's likely to get the Nobel Prize for it. Stephen bet that black holes were not real. And the logic of Stephen was that if he spent his life working on something that wasn't real, he'd at least want to win a bet. So he kind of paid up on this bet some years ago. So Stephen and Roger Penrose have worked on black holes really since the 1960s and 1970s, so 40 to 50 years. So in parallel with all this astrophysics that I've been describing, there are a lot of people in maths departments who've been thinking about black holes, because there are a lot of really puzzling sort of properties. So on the right hand side is yet another picture of the black hole. So it's the same kind of picture as I showed before, that we think of the black hole as curving the space-time around it so much that if you fall into the interior region, so now it's the region behind the orange bit, is this bit here, that's the place where you get stuck. But then, if you kind of now take very seriously what Karl Schwarzschild did in 1916, all this analytic continuation of things, and you say, well, what happens, you say, okay, I accept that I've fallen inside the black hole, you can really do that. And you say, well, what happens down here, what's going on? So what does the theory tell us? What does the maths tell us? Well, according to the Schwarzschild analysis, the space-time curvature becomes very, very large, even larger as you go down right into the inside. And at r equals 0, so in the matrix I wrote you, there was something special happening when r took the special value 2gm over c squared. But there was also something happening at r equals 0. You also had 1 over zeros in your metric in various places. So the Schwarzschild metric is ill-defined, and you can't play coordinate tricks and actually do that. It's really a singularity in the sense of, again, that we teach in complex variable theory. So it's a singularity in the sense that there's a pole in curvature. Again, for those who haven't done complex variable theory yet, you'll come to this. And so this very notation that you hear sometimes in movies, science fiction movies, and you will see in popular science, is actually directly inherited from the maths terminology, actually. It's really a singularity in exactly the same sense as we mean in complex analysis. So this is kind of a puzzle, because essentially we get we don't get sensible answers at r equals 0. So at the very center of space-time, r equals 0, color coordinates, what's going on. Okay. Now, why do people, and also why do people think it's important? You know, is this just a kind of maths technicality or not? So again, we go back to the beginning of the 20th century. Beginning of the 20th century, people didn't understand atomic physics very well. And the thing that really puzzled people was when, you know, after Rutherford did experiments showing that we have an atomic structure which is the positively charged nucleus at the center, surrounded by electrons. People didn't understand why the electrons just wouldn't fall into the positively charged nucleus. That, you know, they would attract each other. And, you know, what people realized was that, you know, you needed something, classical physics wasn't enough, you needed quantum physics. You have, you know, discrete orbits and things like that. You know, that's in a sense, some version of this is what you learn in GCSE science. So, the infinite answers that we would have got from classical physics were a sign that there was really something missing in our physics theory. And so the black hole singularity is again taken as an indication that Einstein's theory, which was a classical theory, you know, it's just a theory with classical equations, is not enough. You need something more than that. And so, you know, when you get puzzles in classical physics, like the puzzles of atomic structure, you need quantum mechanics. We found a puzzle in general relativity, which is classical physics. There's a puzzle here, we probably need some quantum mechanics. Now, back in 1974, Stephen Hawking also discovered that quantum physics comes in at the event horizon itself. So, in quantum physics, again, you know, there's not time for sort of a lot of discussion of quantum physics here. Quantum uncertainty allows particles to escape, so things are not certain in quantum physics. You know, there's a certain probability that things can escape, and that was what he figured out. And so black holes do actually give out particles really slowly. They, you know, the actual rate at which they allow particles to escape is too slow to be seen by telescopes. So the black holes still look black for a telescope, but if you could watch long enough, you would actually be able to count some particles coming out. That's what he's known for. So this thing is called Hawking radiation, and that's probably his biggest discovery. Now, whenever you have an object which has temperature, a black hole has a temperature which is very, very low, so it's 10 to the minus 8 in, you know, Kelvin measured in solar units. So a black hole with the same mass as our sun would have a temperature of 10 to the minus 8 kelvins. That's really very small, because background temperature of the universe is about 3 kelvins. Whenever you have something that has temperature, you also get an entropy. And this guy, Einstein and Stephen Hawking, realized that the black hole has a huge entropy. So this number is huge, 10 to the 77 in solar mass units. So what is an entropy? Again, we can define it in math concepts, but for here, the easiest way to think about an entropy is it's basically counting the number of different quantum configurations the black hole can have. So there's a formula on Boltzmann's graph, which is that the entropy S is Boltzmann constants times the log of the number of configurations. This is his graph. So somehow a black hole has an enormous number of different quantum configurations. And this is really puzzling because I gave you a black hole solution which was really simple. I just said, okay, here's a black hole solution, there's one solution. I didn't say, well, I've got 10 to the 77 different solutions. I just got one solution. So that's a long-standing puzzle. And in fact, it's not just, you know, my ad hoc, well, I've only found, you might say, well, I wasn't good enough at solving the equations, because there are actually a lot of mathematical physicists, again, this is a guy called Werner Israel, who proved very, very rigorous results for mathematics, that, you know, the number of solutions of the equations, you know, there were only a finite number of solutions of the equations. So there's very small. So these theorems say that the black hole is going to be described in the same way, regardless of how it was formed, regardless of how it acquired its mass. So if I took a star and I threw different things into it and eventually turned into a black hole, eventually the black hole would be described by the same solution of Einstein's equations. And then according to Stephen Hawking, it would eventually leak out particles and evaporate into radiation. So then how would we be able So you got your black hole, you throw obsolete computers into it, you throw obsolete textbooks into it. It evaporates slowly, it gets smaller. If you wait long enough, like billions of years, it gradually gives out Hawking radiation, and then it's eventually turned into heat. But then the problem is that, from the end point, we can't kind of trace back the steps and say what happened at the beginning. We seem to end up with the same amount of, the same heat. And this is kind of a puzzle, right? Because usually in physics, we would assume that we would be able to we might not be able to do it practically because it's too complicated, but you'd assume that you'd be able to trace things back in time. Now, how does this work normally? So, an example people often use is, something else which has a temperature. The air in this room, we can describe it by its temperature and its pressure. And it also has an entropy that counts the number of different configurations of molecules. In this case, we actually understand what the different configurations are. So many different effects could change the temperature and the pressure in the same way, but in principle you could actually track the position of the air molecules. So these two configurations here, this is a gas in the room. This could have the same two temperatures, but we can actually see just visually that the molecules are in different places. Yeah. So somehow what we have with black holes is a case where we know that they must have different quantum configurations, but we don't know what they look like. We've got this description of their temperature and their mass and their general properties, but we don't have a description of the different quantum, the different molecular configuration of black holes. So where the title of the talk comes in the last 5 minutes, is the emerging consensus over the last few years is that there is indeed, we cannot just use this analytic continuation of the Schwarzschild solution. So in a sense, we've gone full circle. In 1916, people didn't take it seriously. Through most of the 20th century, they said, well, we should take seriously analytically continuing the solution. And now we realize, hang on, actually, there's something more complicated happening. So there are all kinds of things being thought about. So if we go back to the Einstein equations, as I said, there were these theorems from Israel from the 1960s which said that there are only a finite number of solutions, a small number of solutions of Einstein's equations that goes on black holes. And they were absolutely mathematically rigorous theorems. But any theorem is based on certain assumptions. And the assumptions are nowadays perceived not to have been so reasonable as they were thought at the time. So some of the assumptions, a very reasonable assumption was that we seem to have 3 dimensions in the world. But actually, most theories of quantum physics predict that there are more than 3 dimensions. So that makes a difference to the theorems. It turns out that the maths works really differently if you have more than 3 dimensions. There are more technical assumptions about the kinds of energy and things like that. Okay. So in the news this year, Stephen Hawking has been in the news quite a bit actually about something called hair on black holes. So shown on the right-hand side is his collaborators, Malcolm Perry from Cambridge and Emma Stronger from Harvard. So what they've been discussing is that after all, there are actually other black hole solutions to Einstein equations. So we can't just describe black holes by the mass. There are other parameters as well, and they refer to this as hair on the black hole horizon. So somehow we thought there were about 10 to 77 different types of different configurations of black holes. So they have tracked down some of the different configurations. And as an illustration, I think the maths on this slide is completely incomprehensible, but that's what they're illustrating, the kind of equation that they have found. But at the same time that the hair they found is not 10 to the 77 enough to account for 10 to the 77 configurations. So that's not quite enough. So there's a more general idea that goes on. So I said at the beginning, when we went from that to, when we learned to understand atomic physics, we really needed a new idea in terms of quantum physics and quantization of orbits and things like that. So that somehow this part of the black hole diagram that we had from just extending the solutions of Einstein's equations is not quite right. The idea is that there are many different ways of doing this, 10 to the 77 different ways of doing it. So this at the back of the room, if you just looked at this from the top, this would look kind of the same as this. But as you come close up, you can see that the fuzz is sort of different. And the idea is that there's 10 to the 77 different kinds of ways of different configurations of the black hole. Now, one sort of way to think about that, which is probably the easiest way to think about it, is that on the surface of the black hole itself, on the spherical surface, it's sort of like a giant computer hard disk. So you can think of it storing information in zeros and ones. There's one bit of information per Planck unit of area, and there's about 10 to the 77 bits of information in total. That's the idea. And the analog of knowing the configuration of all the other molecules in the room will be to know the precise state, precisely all these ones and zeros in what order there are. Anything that falls into the black hole modifies the state of the hard disk. So an old computer going in or a textbook going in changes the state in a different way. And what they found last year and early this year is very special states of this hard disk. So it's imagine arranging these zeros and ones in nice symmetric patterns. That's where the symmetries come in. So they've arranged the sort of information in symmetric patterns. And when something falls in, it changes the pattern from kind of one symmetry pattern to another symmetry pattern. So the big question is, how do we describe this general state of the quantum hard drive? Solutions of Einstein's equations on their own are not sufficient. You need something beyond that, which people kind of use to call quantum geometry. And this surface will keep track of everything. It will keep track of orders. Okay, let me skip this. So the black holes lead us to this very new idea. So this idea of holography is that somehow on the black hole surface it's behaving like a giant computer hard disk. So, and the configuration of that hard disk is telling us about the back history of the black hole being formed, the back history of the universe. If you kind of could measure all the state of that hard disk, you know everything. Now that we can actually do experiments with things like LIGO, and we see black holes colliding, you might actually be able to see not just the approximate description of black holes, which the Schwarzschild solution gave you, but this detailed, these sort of little, in a sense, little symmetry patterns on the surface of the black hole. So that's what people are looking at and watching at. So the picture on the right-hand side is actually LIGO's successor in space. This is called ELISA. So this is gravitational waves detector, which is based up in space. And so they would actually be extremely good at looking at this symmetry too. Now, in the second half of the talk, I've used more physics language because it's easier to explain in physics language than maths language. It turns out that the required mathematics you need for this is extremely new. So this idea of quantum geometry, whatever it is new mathematics shaped by physics. So there's a kind of a new terminology, I guess, at the moment, called mathematics. This is mathematics inspired by and shaped by physics. Yeah, so it's teaching, mathematicians, pure mathematicians, new concepts and that stuff. And we definitely need something like this to describe it. Let me stop here. Sorry, I'm a little bit late.
Does anyone have any questions? In that case, I will.
Well, I'm not sure if I understood exactly what the solution intends and so but they said that mass is not only parameter relations.
That's right.
So what would be?
So again, it would be that at the black hole event horizon itself, that it's not really spherically symmetric anymore. So there's it sort of breaks the spherical symmetry, and in my in terms of there being like a hard disk at the horizon, it's like you've kind of excited certain parts of it. So I could kind of do a light show, sort of saying that different bits of different bits of the spherical surface of the horizon are in a sense, you know, excited. They're looking different. They're different shape.
And also, so for example, consider that so when two black holes like they collide and
Yep.
say like they emit a lot of gravitational waves, so
Yep.
it means that other things keep being attracted to this black hole more and more, right?
That's
so it's
right.
gonna be to the point that the whole universe is colliding to a black hole.
Well, you're partially correct. So different galaxies, every galaxy has at its center at least one super heavy black hole. And you're right that eventually that will pull everything into the center of the galaxy. And then when these galaxies collide with each other, the black holes merge and then they pull everything around them. So indeed it would happen eventually that many of the galaxies would kind of turn into very super heavy black holes. But then there are whole voids in the universe where there's nothing. And so they would be too far away, you know, from everything else to pull everything in. So there will be a stage in the history of the universe where we have some super heavy black holes and not much else. And then the universe is expanding, so these heavy black holes are kind of being pulled further and further away from each other. So yeah, there's a depressing sort of future for the universe, where everything is kind of super heavy black holes for a while, which are isolated, and then they kind of just decay away into Hawking radiation, and then that radiation gets sort of stretched and expanded, gets colder and colder, and we have a long death for the universe, which is not what happens in Doctor Who. So I, you know, go to watch that instead. It's more cheerful.
Although I guess we may rest assured in the knowledge that all the information will be kept.
That's right, yes. So for many years people thought, and Stephen Hawking himself and Gerard Toft, another Nobel Prize winner, thought that maybe physics didn't actually keep that information. And now the solution is yes it does, and somehow we missed something. The black hole really does have these configurations, and what do they look like? That's the switch of the question. And in a sense, Stephen has conceded by himself writing papers that say, hang on, some of the configurations look like this.
Go for it.
If black holes are actually puzzles and they have no event horizon, what does that mean for their observable properties like
Well, that
or gravitational lensing?
that is literally the sort of million-dollar question, actually, in the sense that obviously if you could find something which was nicely detectable and it was found to distinguish between a black hole and a fuzzball, that would for sure be, you know, a Nobel Prize and more than that. So that's what people like us actually work on. If we get really lucky and we have a nice clean fuzzball fairly near us, we may actually see differences in gravitational lensing. Generically, the differences are really, really small. So, and the differences in gravitational waves are really small. So you've got to kind of get clever and predict something which would not be seen with just the naive Einstein picture. But it's definitely the million-dollar question which people are thinking about.
Go for it.
As a black hole is sort of actually spherical, the amount of information you need to store whatever went into it grow faster than the natural surface.
So the information grows. I mean, this is part of, in a sense, the built into the modern theories. The amount of information grows as the area of the surface. If we have something that's not spherically symmetric, the surface is not a sphere, it's like this kind of, you know, oblate spheroid. But again, the information goes with the area of that surface. Yeah, and that's in a sense built into the modern quantum theories of black holes.
Okay, looking at the Schwarzschild solution, why don't you call the element the mass?
So that's several lectures in a general relativity course to explain to you how we go from the Einstein relativity description to the Newtonian description of gravity. So the Newtonian description of gravity would use gravitational potential and a gravitational field. So when we look at when we go to that Newtonian description, so when we go away from the black hole and we look at the effect of gravitational potential, it behaves like Gm over r, which is the gravitational potential a Newtonian theory of something which is due to mass m. So that's, and essentially that parameter m becomes the parameter in the gravitational potential which is caused away from the black hole. But it's got, of course, some lectures and a GR course to explain how to go from the relativistic